Imagine this. A queen passes away, but instead of a simple will, she leaves behind a high-stakes puzzle. The prize? A massive fortune in precious stones. But here's the catch. To claim it, you have to be the very first person to solve the riddle she left behind. This is the story of that puzzle.
So, let's meet our key players. This is Queen Ratna Manjuri. Now, she was clever. To avoid a family feud over her wealth, she didn't just hand it all to her son, Koisnam. Oh no! Instead, she set up a test. So picture this, a grand hall where Koisnam and 99 of his relatives are gathered. You can just feel the tension in the air, right? Everyone waiting to face her final brilliant challenge.
And the stakes? They could not be higher. The will made it perfectly clear. If you all solve it together, the fortune gets shared. But if you're the first one to crack it, you keep everything, the whole shebang. So this wasn't just a friendly brain teaser, it was an all-out race.
Okay, so the Queen's minister leads all 100 relatives into this secret room, and lining the walls are 100 identical closed lockers. He explains that the puzzle is a game of logic, and every single person in that room has a part to play in revealing the final code to the fortune.
The rules seem simple, but trust me, they're deceptively complex. Here's how it goes. Person number 1 walks down the line and opens every single locker. Easy enough. Then, person number 2 comes along and toggles every second locker. Now, toggle is the key word here. It means if a locker is open, they close it. If it's closed, they open it. Then person 3 toggles every third locker, person 4 every fourth, and this continues all the way up to person 100.
You can actually see the pattern starting to form right here. Let's just trace what happens to, say, locker number 4. Person 1 opens it, person 2 closes it, person 3 skips it completely, and then person 4 opens it again, and ends up open. But now, look over at locker number 6. It gets toggled by people 1, 2, 3, and 6, 4 times, and it ends up closed. What's going on here?
And that, right there, is the multi-million-dollar question. Before anyone even took a single step, Koisnam realized he already knew the answer. How? What pattern did he spot that all 99 of his relatives completely missed? The key to the whole thing is hidden in the numbers of the lockers that are left open.
You see, Koisnam's brilliant insight was that this wasn't about tracking 100 people running around a room. No. The real secret was hidden in the mathematics of the locker numbers themselves.
So it all boils down to this one crucial point. Every locker starts out closed. If it gets toggled once, it's open. Toggle it again, it's closed. A third time, it's open again. See the pattern? An odd number of toggles means the locker is left open. An even number means it's closed. Suddenly, the problem is much simpler. Which lockers get toggled an odd number of times?
And this is where a little bit of math vocabulary comes into play. Factors. A locker is only toggled by a person if that person's number is a factor of the locker's number. So for locker number 6, the people who touch it are persons 1, 2, 3, and 6. The number of times any locker is toggled is simply its total number of factors.
This slide just lays it all out perfectly. On the left, you've got locker number 6. It has 4 factors, 1, 2, 3, and 6. That's an even number, so it ends up closed. But now look at the right side, locker number 9. It's toggled by persons 1, 3, and 9. That's only 3 factors, an odd number, so it stays open. The real challenge then is to figure out all the numbers from 1 to 100 that have an odd number of factors.
And that one simple question, which numbers have an odd number of factors, that leads directly to the winning insight. It's the key that unlocks the whole puzzle.
Think about it for a second. Factors almost always come in pairs, right? For a number like 6, you've got the pair 1 and 6. They multiply to make 6. Then you have the pair 2 and 3. This pairing is why most numbers have an even total of factors. But what makes a number like 9 so different?
Well, the answer is that it's a perfect square. A square number is just what you get when you multiply a whole number by itself. Simple as that. And here it is, the big aha moment. For a perfect square like 9, the factors are 1 and 9, and then there's 3. But who's the partner for 3? Well, it's itself. 3 times 3 is 9. Because that one factor is its own partner, it doesn't create a new pair. It breaks the even pattern and gives you an odd total number of factors. That's the secret.
So the lockers that will be left standing open are all the perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. These 10 numbers, They hold the first part of the code to that giant fortune.
But hold on, the queen was thorough. As Koisnam walks up to these 10 open lockers, he finds one last note tucked inside, one final layer to her brilliant puzzle. The game isn't quite over yet.
The final clue reads, the passcode consists of the first 5 locker numbers that were touched exactly twice. Whoa, the puzzle just shifted gears. We're not looking for an odd number of touches anymore. Now we need numbers that were touched exactly 2 times. So which numbers have exactly 2 factors?
And the answer, of course, is a prime number. That's the very definition of a prime. A number that has only 2 factors, 1 and itself. These are the numbers that were touched exactly twice, once by person 1 and once by the person whose number matched the locker's number.
And just like that, Koisnam has the final key, the first 5 prime numbers. He walks up, punches in the code, 2, 3, 5, 7, and 11. The safe clicks open, and the queen's entire fortune of precious stones is his. He solved the puzzle first.
You know, the Queen's puzzle is such a great example of how really complex-looking problems can have these simple, elegant solutions hiding right under our noses. It kind of makes you wonder, doesn't it? What other mathematical secrets are all around us, just waiting for a curious mind to come along and crack the code?